the simple gas law. So we've talked about how gases are affected by temperature, pressure, volume, and the number of particles, so moles. And then there's been some gas laws derived from holding a few constant and seeing how the others affect each other. So these gas laws are stated over here. We know that the ideal gas law comes from trying to see how a gas behaves under the conditions of wanting us to see it ideally, where the gas constant is in liters, atmospheres, mole, and Kelvin. And then all the other gas laws are when something is held constant, or our last one right here is when we're looking at just a mixture of gases. So the best way to determine problems with gas laws is to kind of see what you have and what variables you're given, figure out what equation you need to use, and then just plug everything in. So let's look at this first one. When Whitney has her asthma attack, oxygen was delivered through a face mask. The gauge on a 12-liter, so here's a good chunk of information. I'm going to already write that. I'm given a volume, the first one, of 12 liters. Tank of compressed oxygen reads 3,800 millimeter mercury. There's my first pressure. How many liters, now I know what I want, my second volume, would this oxygen occupy at a pressure of 0.75 atm? Perfect. So I have pressure and pressure, volume, and I want another volume. So the gas law that would make sense for me to use is Boyle's law. So P1 V1 is equal to P2 V2. I have my P1, my V1, and my P2, and I want to solve for V2. Now, an important thing to notice here is that this unit of pressure is millimeter mercury, and this is atmosphere, and they're not the same unit. And you want to make sure that they're the same unit. Otherwise, they wouldn't cancel out, and you wouldn't just be left with liters. You don't always have to worry about converting. That's only in cases where it tells you specifically what unit you want, or if your units wouldn't cancel out properly if you didn't convert. So here we first have to convert. It doesn't matter if you convert millimeter mercury to atmospheres or go the other way around. I'm going to convert 3,800 millimeter mercury to atmospheres. My conversion factor is written right here. Since I want atmospheres, the 1 atm is going to go on the top. 760 millimeter mercury will go on the bottom. And that equals to 5 atmospheres. And now you have everything you need to plug it in. So you have, for your first pressure, which was 5 atmospheres, you converted it, times volume, 12 liters, is equal to your second pressure, 0.75 atmospheres, times your second volume. Now, because you want to solve for V2, you have to get your 0.75 on the other side. So you divide both sides by 0.75 atmospheres, which will cancel this out, and you'll be left with that. V2 is equal to 5 atmospheres times 12 divided by 0.75, which gives you 80 liters. Now, how many significant figures do we want? We have 2 here, 2 here, and 2 here. So I need to put a little period by the 80 to make it 2 sig figs. Let's keep going. A helium gas is used to inflate the abdomen during laparoscopic surgery. A sample of helium gas has a volume, there we go, first information, given volume, 5.4 liters, and a temperature of 15 degrees Celsius. What is the final volume? V final, V2 to be consistent. If the gas temperature is raised to 42 degrees Celsius. So here I'm given volume volume, temperature, and I want another temperature. So this time, my Charles's law is going to come into play. So I'm going to use this law. So I have V1 over T1 is equal to V2 over T2. Now you can first plug things in and then solve, or you can rearrange your equation. So I have my first volume, which is 5.4 liters, over my first temperature, which was 15 degrees Celsius. Note that I'm not converting because the units will cancel. V2, which I don't know, over 42 degrees Celsius. Now here, because it's a fraction to isolate for V2, you have to cross multiply, which gives you this. So you have 5.4 liters times 42 degrees Celsius is equal to V2 times 15 degrees Celsius. And then, since you want to get the V2 by itself, you divide both sides by 15. And then you'll get your second volume. So 5.40 times 42 divided by 15, which should be, just checking my work, 5.4 times 42 divided by 15 gives you 15.12, and you want 2 sig figs, so 15 liters. Let's move on. A tank contains isoflurane, an inhaled anesthetic, as a pressure of 1.8 atm and 5 degrees Celsius. So what am I given here? Given pressure 1.8 atmospheres, temperature 5 degrees Celsius. What is the pressure? So I want another pressure, so these are going to be my first ones. And a second temperature is 22 degrees Celsius. So now I have pressure, pressure, and temperature, so I'm going to use Gay-Lussac's law. So P1 over T1 is equal to P2 over T2. So this time, let's first rearrange the equation. We want this variable. So just like before, you cross multiply. P1 T2 is equal to P2 T1. And then, since you want to solve for P2, you divide both sides by T1. And your new equation would be P2 is equal to P1 T2 over T1. And then you can plug it in. Same type of idea, but this time you rearrange your variables first before plugging things in. So first pressure is 1.8 atmospheres times second temperature, 22 degrees Celsius, divided by your first temperature, which is 5 degrees Celsius. And then your second pressure is 1.8 times 22 divided by 5. So 7.92. You want 1 sig fig, because 5 degrees Celsius, this is just 1 sig fig. So 8 degrees Celsius is the answer. And it's not Celsius, whoops, it is atmospheres, because Celsius cancels. So 8 atm. Alrighty, let's keep going. So here we have a 124 milliliter bubble. So volume, 124 milliliters of hot gases at 212 degrees Celsius. Okay, 212, so I have a temperature, and 1.80 atmospheres. Okay, so I have another pressure. From an active volcano. What is the final temperature? So I want T2 of the gas in the bubble is the final volume. So these are all my ones. Then my V2 is 128 milliliters. And the pressure is 0.8 atmospheres. So I have pressure, volume, and temperature. So I'm using my combined gas law. And here we're solving for T2. So let's rearrange the equation first. So again, whenever you have a fraction, just cross multiply to get rid of the fraction. So this gives you P1 V1 T2 is equal to P2 V2 T1. You want T2, so you're going to divide the sides by P1 V1, which gets rid of that. And then you come out with that T2 is equal to P2 V2 T1 divided by P1 V1. Then you have everything set up. When you're looking at your values, there does not need to be anything that has to be converted, so you just plug in. So your second pressure is 0.8 atmospheres. Volume is 128 milliliters. Your first temperature was 212 degrees Celsius. And then you divide all that by your first pressure, which was 1.8 atm. And your first volume, which was 124 milliliters. You can even double check. Milliliters cancel, ATM cancels. You want a temperature, and you'll be left with degrees Celsius, so your setup will work out. And you just multiply 0.8 times 128 times 212. Divide that by 1.8. That's multiplied to 124. And you should get 97 degrees Celsius. Let's see how many sig figs we want. We want 3, so 97.3. And you can always double check if your answer makes sense. So we realized that the units made sense, but I could have flipped the wrong pressures and volumes. So if you read the question, it says that a 124 bubble of hot gases at 212 degrees Celsius and 1.8 atmospheres is emitted. So that means things were let go. Particles were left. Hot gases were left. What is the final temperature when the final volume is 128 and the pressure is 0.8? So the pressure went down, volume increased, things were emitted, so your temperature should be lower, which it is. Just another way to apply the concepts of gases to make sure you're on the right track. A weather balloon with a volume of 44 liters is filled with 2 moles of helium. What is the final volume if 3 moles of helium gas are added to give a total of 5 moles? So we have volume, 44 liters, initial moles of 2, and then final moles of 5, not 3, because 3 was added. And we want, what do we want again? Final volume. So this brings us up to Avogadro's law right here. That's what we want now. So we have V1, N1, V2, N2. You want V1. So again, you can cross multiply and isolate. V1, N2 is equal to V2, N1. You want to solve for V2, so your N1 has to go to the next side. So your second volume is equal to your first volume times your moles divided by your initial moles. You can plug everything in. 44 liters times 5 moles divided by 2 moles. So if your moles went up so significantly, what should happen to your volume? Your volume should also increase. So this is another way that you can check. You know you're going to get liters, and your volume should be bigger because 44 liters when you had 2 moles of particles. Now, if you have 5 moles, those should hit the walls of the container and expand the volume, so your volume should be greater. So wait for you to see if your numbers make sense. When you plug that in, you get 110 liters. We want 2 sig figs, and so we're finished. All right. What is the volume of 64 grams of O2 gas at STP? So what is STP? That stands for standard temperature pressure. And whenever we have given STP, we know the values. We know that pressure is equal to 1 atm. Temperature is equal to 273.15 Kelvin. These are our standard conditions. So we want volume. And we're given mass of 64 grams. we're given our pressure of 1 atm, and we're also given temperature of 273.15 Kelvin. So I'm going to erase this for a little bit more room. Well, now what gas law am I going to use? So let's look up here. Well, I only have one pressure, one temperature. I want volume. So none of these gas laws will work regardless because you don't have more than one. It's not going to be the mixtures because you don't have a mixture, so it has to be ideal gas. So first, let's write the equation down to see how to solve it. PV is equal to nRT. Well, R we always know. R is 0.08206 liters atmospheres mole Kelvin. So we have R, we have temperature, we have pressure, and we want volume. So how do we get moles? We need to figure out how to get moles so that we can solve for the volume using ideal gas. Well, I'm given 64 grams of O2 gas. And I know I can always go from grams to moles using molar mass. So I'm first going to convert. So 64.0 grams O2 and divide that by the molar mass, which is 32.01 grams. And that gives me 64 divided by 32.01 is 1.99 moles. Now, if I go back to my PV equals nRT, I have everything to solve for the volume. So I divide both sides by the pressure and get that the volume is equal to nRT over P. Now, you want to make sure all your units relate to your gas constant. Well, I have Kelvin, I have atmospheres, I have moles. I should be left with liters. So then you plug it in. 1.99 moles times the R constant, 0.08206 liters atmospheres mole Kelvin, times the temperature, 273.15 Kelvin. And then you divide that whole thing by your pressure, which is 1 atmospheres. I'm totally running out of room, but that's fine. So then you see, all right, let's double check. Moles cancel out, atmospheres cancel, Kelvin cancel. You're left with liters. I'll write the answer up here. You can just multiply. 1.99 times 0.08206 times 273.15. Divide that by 1, which gives you 44.6. You want 3 sig figs, so 44.6 liters is your answer. Alrighty, let's look at one more example for the simple gas laws. So, we have here butane is used as a fuel camping for stoves. If you have 108 milliliters, so we're given a volume of 108 mils of butane gas at 715 millimeter mercury. So pressure, 715 millimeter mercury. Temperature, 25 degrees Celsius. What is the mass? Okay, so we want grams. We're only given one volume, one pressure, and one temperature. So none of our simple gas laws are going to work because we have to have more. So again, we need to use ideal gas law. How are we going to apply that? So ideal gas is PV is equal to nRT. Well, what values do I have? I have my pressure. I have a volume. I have a temperature. I always know R. So if I use ideal gas law, I can solve for moles. Okay, well, what is that going to help me with? So I know, I'm going to write a little note. Can calculate moles. I know I can do that for sure. Well, I want mass, and I know my formula. I can use the moles to convert moles to grams using molar mass. Similar to the problem before, just different arrangement. So I'm going to first solve for my moles. Now, since I know the unit of R, I have to make sure that everything is in the right unit. R is 0.08206 liters, atmospheres, mole, Kelvin. So if I want moles, liters, atmospheres, and kelvins have to cancel. All my units are not in those units, so I have to convert. So let's see that. Alrighty. My milliliters have to convert to liters. So there's 1,000 milliliters in a liter. That gives me 0.108 liters. There's 760 millimeter mercury in 1 atmosphere. So to divide that by 760 millimeter mercury, which will give me 715 divided by 760, 0.94 atmospheres. And then 25 plus 273.15 is equal to 298.15 Kelvin. And now I have everything the way that I need so that I can solve. So if I want N, I need to divide both sides by RT. So then I get N is equal to PV divided by RT. And you plug everything in. Pressure is 0.94 atm. Volume is 0.108 liters. Divide that by 0.08206 liters, atmospheres, mole, Kelvin. And T, which was 298.15 Kelvin. Then N is equal to 0.00414. Now I'm not finished because I wanted grams. So then I first have to find my molar mass of butane. So 4 carbons plus 10 hydrogens, which is 4 times the molar mass of carbon, 12.01 grams per mole, plus 10 times 1.008 grams per mole. And that comes out to be 58.12. Now I use that to convert to grams. So I have 0.00414 moles and multiply that to the molar mass. And that is equal to 0.24 grams. I want two sig figs, so 0.24 grams is the answer of C4H10. So the best way to go around solving all of these different equations is to just look at the variables that you're given and isolate for whichever equation you need. Once you determine that you don't have more than one pressure, volume, or temperature, or moles of gas, ideal gas is a good bet to go. Whenever it says that you have a mixture, you'll have to go with the mixture. So then the next step is, okay, are all my units the way that I need? Do I have to cancel anything out? Well, you only do, like in our first one, if they wouldn't cancel out. Or in the ideal gas law equations, if they don't add up to the units of the gas